All right, I'm going to try to make this a little faster than the one before. I know you know this stuff. It does get a little bit more complicated here. So I'm going to skip over slides that you can write down and read. I don't need to read them to you. Okay, so this first one in 6.5, this slide is just telling you all of the rules of simplifying radicals. This is all the stuff that we worked on in those skill sets. So this is kind of like your checklist. We are only going to concentrate on the first 3 rules. Got to pull out a perfect. If there's a perfect factor inside the radicand, you have to get rid of it. Can't leave it there. You got to get rid of the fractions underneath the radicand, and you can't leave a radical in the denominator. This last rule we're going to deal with first thing, second semester. Okay, so if you need to pause, write those down. We're good to go. Same thing here, this slide, I'm not going to read it to you, but these are the 2 properties that we use to simplify. The power property allows us to put together, take apart, and same thing with the quotient property. It allows us to take a fraction and break it into 2 separate or vice versa. So we're just going to practice simplifying again. It's been a while since we did these. So these first 4 examples are where you have to pull a perfect out. Okay, so 24 is not perfect. If you put it in your calculator, you're going to get an ugly decimal. So we break it into a perfect 4 and a non-perfect 6. And then we just use the shortcut with the variables. So remember there's a little 2 here for the variables. I like the approach of having an area out in front of the radical, and then because they're not perfect, you're going to have some stuff underneath the radical in the end. The square root of 4 becomes a 2 on the outside. The square root of 6 goes inside. And then we divide the variables just like before. You say, how many times does 2 go into 3? It goes into it 1 time, but with 1 remaining. How many times does 2 divide into 2? 1 time. So I look at those, and again, those absolute values. A to the 3rd was odd, so we don't have to worry about that. But we went from a b squared, which was even, to a b that's odd, so we put absolute values around it. And that's it. That is the simplified form of that radical. Number 2, all of this is extended underneath the radical. 64 is perfect, but my variables are not. So again, I'm going to leave space out in front for the perfect information, and then the non-perfect goes after it. So square root of 64 becomes 8. Square root of a squared becomes a. Square root of b cubed, you take the 2 that's sitting out here, and you say, how many times does 2 go into 3? It goes into it once with 1 remaining. And there's not enough to divide c, so c just goes inside. A squared went from an even to an odd, so we put absolute value signs around it. Little cube root. Okay, you may want to get your list of perfects out for tomorrow. They're in your skill sets. So 54 is not a perfect cube, but 27 is. And 27 times 2 makes 54, and then we'll just leave the variables inside here. So a line out in front, a space out in front for the perfect stuff, and then a radical afterward. Cube root of 27 is 3. Cube root of 2 goes inside. Cube root of a cubed is a with no remaining, and 3 goes into 7 2 times, so b squared with 1b remaining underneath. So you look at the original problem, and they were both odd to begin with, so this is all we got to do here. And the next one, we've got 2 radicals, so let's put them together first. So 10 times 40 is 400, x squared times x is x cubed, and y times y cubed is y to the 4th. And so when we put them, 400 is perfect of 20. X squared becomes, or x cubed becomes an x with an x left over, and y to the 4th becomes y squared. And there we are. So that is an example, or those 4 are examples of where you had to take the perfect out. The next slide involves all of the fractions. How do you get rid of fractions underneath the radicand? So the quotient property allows us to separate it. So if you have a square root of 5/4, it becomes the square root of 5 over the square root of 4, and the square root of 4 cleans up nicely to 2. So you have the square root of 5 over 2. Number 6, you get the cube root of 3 over the cube root of 8. Cube root of 3 just stays cube root of 3. Cube root of 8 becomes 2. And number 7, there's several different ways to do number 7. Probably the easiest way, my favorite, is to divide. And so you have 20 divided by 2 is 10. And then break 8 into 4 and 2. Keep root 2. And so I rewrote 8 as a product of 4 and 2. I divided the 20 by 2, and these root 2's cancel. Square root of 4 becomes 2, and 10 times 2 is 20. But there's more than one way to do that, but that is probably the quickest, the least amount of work. Okay? In all 3 of those examples, the denominator just cleaned up on its own. So the next part we're going to talk about is how you get rid of the denominator. Oh, not yet. I lied. We're going to multiply. And then after we multiply, we'll learn how to clean up the denominator with a radical. When we multiply, outside number gets multiplied by outside number, inside times inside. So again, you guys can pause, replay, whatever you got to do to get these down. 3 times 4 makes 12, and 2 times 10 makes 20. So this simplifies to 12 root 20, but there's a perfect inside 20. 20 becomes 4 and 5. The 4 turns into a 2. The 12 and 2 make 24. So we end up with 24 root 5. Number 9, we're going to distribute. There's really a 1 out in front here that I can multiply the 4 by. So outside times outside gives me 4. Inside gives me root 81. Distribute. 4 times 4 is 16. Root 3 makes root 9. These are both perfect. Square root of 81 is 9. 4 times 9 is 36. Square root of 9 is 3. 3 times 16 is 48. We have 36 plus 48 gives me 84. And that's your answer. That's multiplication. Now we're going to learn how to rationalize the denominator. When we rationalize the denominator, we are actually making the denominator a rational number. When you have a radical in the denominator, like the square root of 3, it's irrational. So when you say we're rationalizing the denominator, we are making the denominator a rational number. So right now in number 10, we have a problem with the square root of 3. That's really the only problem. So we've been doing this all year. Whatever you do the denominator, we can do the numerator to clean up. So we're going to multiply a square root of 3 by another square root of 3 to make it a perfect square. So I get 5 root 3 over 2 root 9. Well, 2 root 9, the 9 becomes a 3. 2 times 3 is 6. So 5 root 3 over 6. Number 11, let's clean it up before we actually try to rationalize the denominator. So split it up, square root of 4 over square root of AB squared. Square root of 4 becomes a 2. And I can clean up that radical. The A stays, but I can take a B out. Has absolute value signs around it. And then you got the square root of A. So the only issue we have is that square root of A. So if I multiply both top and bottom by the square root of A, it'll become a perfect square. And so we end up with 2 root A all over absolute value of B root A squared. And then you get the A on the outside. This is where those those absolute values get a little tricky. So I don't even know if the book puts them in there or not anymore. I think it goes off of the original problem, because you could argue that we went from an A squared to an A that's even. But if you look at the original problem, A was to the first power. So we really don't have to worry about it there. And that's your answer. Number 12, cube roots. These are the ones that always tricked you. Okay, when you have a cube root of these things, it's not just multiplied by itself, because that'll give you a perfect square. We got to multiply it by itself squared to get a perfect cube. So we separated cube root of 2 over the cube root of 3t. To make that a perfect cube on the bottom, I need to multiply by a cube root of 3 times 3, which is 9. Okay, I have 1 3, I need 2 more. So I'm going to multiply by 3 squared. And to make t a perfect cube, I have 1 t. I need to make it a perfect cube, so I need 2 more. So I multiply top and bottom by cube root of 9t squared. And when you do that, the cube root of 2 times the cube root of 9t squared becomes cube root of 18t squared over the cube root of 27t cubed. All right, I got distracted with a phone call. So cube root of 18t squared over 3t. And that one is good. So that's rationalizing the denominator. Next thing we need to do is add or subtract. Okay, that's where they have to be the like things. So you're just putting them in piles. You just add or subtract a number on the outside. Same radicand, same index. So I'm just going to write down a few. We probably won't do all of these. But let's just try 2 cube root 3, or I'm sorry, 2 square root 3 plus 5 root 2 plus 7 root 3 minus root 2. Just easier to write them down than to type them. So we've got 2 root 3s here. I've got 7 more here. I have a total of 9 root 3s. I have 5 root 2 here, and I subtract 1. I have 4 root 2s. So that's my final answer. You can't do anything else with it. Another one, let's do 4 root 27 plus 3 root 3 minus root 48. Can't do anything right now, but 27 and 48 both have perfects living inside them. So 27 becomes 9 and 3, and 48 becomes 16 and 3. And so now you can see some root 3s. The square root of 9 becomes 3. 4 and 3 make 12, so 12 root 3 plus 3 root 3. And then the 16 becomes a 4, so minus 4 root 3. So you end up with 11 root 3 when it's all said and done. Okay? Multiplication or foiling now. We can FOIL these things. I'll just show you one of these. So we have 2 root 3. Oops, I'm sorry. 12 root 3. My bad. 12 plus root 3. Ooh. Times root 3 plus 6 root 5. So we FOIL. I end up getting 12 root 3 plus 72 root 5 plus root 9, and then plus 6 root 15. Combine like terms. The only thing we can do here, none of them are alike, and so we just make the root 9 a 3 and call it good. If you could, we put things together there. Last part are conjugates. Okay, this is how you rationalize the denominator of a binomial. So I'm not going to read it to you. We're just going to simply go 1 plus 2 root 5 over 6 minus root 5. To get rid of that root 5 in the denominator, you can't multiply both top and bottom by root 5. It'll just keep going back and forth between the 6 and the 5. So to get rid of a 6 minus root 5, you just multiply by the conjugate, which is 6 plus root 5, both top and bottom. Great big foiling problem. So here we go. Let's take care of the top first. You got 1 times 6, which is 6, and 1 times root 5, which is square root of 5. You got 2 times 2 root 5, 6 gives you 12 root 5, and then plus 2 root 25. That's the square root of 5, square root of 5. On the bottom, we end up with 36. Outside will give you a positive 6 root 5. Inside will give you a negative 6 root 5. And last will give you a negative square root of 25. So when we clean this up, I see this 25 up top. Square root of 25 becomes 5. The 2 and 5 make 10. And so the 10 and the 6 make 16. The square root of 5 plus 12 square root of 5 makes 13 root 5. And then these outer and inner terms in the middle cancel. That's why we chose to multiply by the conjugate. Square root of 25 on the bottom becomes 5, but it's really a negative 5. 36 minus 5 is 31. And that is it. That's 6-5 in a nutshell. We are done. We'll do the homework in class tomorrow.